Good afternoon. It's Tapan Bagchi again. I have this series of lectures prepared for you on Six Sigma. Now, one of the procedures or processes that is used in Six Sigma is the improvement process. This step comes along in that DMAIC procedure that we had mentioned in the previous lectures. In this improvement step, what is really required is to be able to find the causes of losses or the causes of high variance and to try to do something about them so that you end up with smaller variance or lower losses. In order to do this, we have to discover some knowledge about the process, and most of this work is empirical. Very rarely you will be able to find a theoretical model which, if you optimize, will give you the optimum result, the best result. So, most of these times we are guided by data collection, we are guided by experiments, we are guided by data analysis and so on and so forth. This is something that we cannot escape. It is actually a key step in the process of DMAC or the Six Sigma approach to improving quality. Now, today what we have for you are the basic tools that have been picked up from statistics and probability. And in order to do that, what I have to do is I have to give you some basic ideas about the concepts in probability and also the concepts in statistics. This is obviously not a complete lecture in probability and statistics, but I'll touch upon all the important concepts there to make sure you get some practice and also you get to see how we utilize these principles to try to tackle real data analysis problems. Now, there are many books available, and a book that is fairly recent and that I found to be quite good is the one that is mentioned right here. You can see the display. It's called Complete Business Statistics, and it's written by Axel and Sandra Payan, and it's published by Tata McGraw-Hill, and the one that I'm using is the 6th edition of the book. You could use almost any other book, but this one I found to be quite readable, and it's got many examples which actually comes from real life. So if you feel like you could buy a book, buy this one, or you could buy some other book. It would be really handy if you have one of these books around to refer to it from time to time, not only for this lecture, but also when you're actually tackling a Six Sigma project. All right, let's begin by going to slide number 1, and the very first thing we have is the title slide, Probability and Statistics in Six Sigma, a review. The objectives of this lecture is going to be lay the statistical groundwork for statistical methods in quality assurance. That I'll try to do in a very broad way. And then, of course, we'd like to be familiar with the tools used in Six Sigma that include SPC, reliability, design of experiments, regression model building, and process optimization. These I'll be touching upon. And just to remind you, if you aspire to get a black belt in Six Sigma, you are required to be familiar with these techniques. These are techniques that actually are part and parcel of the black belt training procedure. So it's not something that have been put here only because it's theoretically complete, but actually these become the tools, these become the devices that you utilize when you approach a project that is to be tackled by Six Sigma. Now, why study probability and statistics? The problem is that most things around us, they have some uncertainty in them. For example, here I've got a system, I've got some kind of a process which is shown by the green box, and notice here this green box is affected by the environmental factors, it's affected by materials coming in, measurement devices and instruments and so on, the methods and technology that is used to do it, some machinery, and also people, obviously. These are all the things that are the input, and they each have an impact. Each of these would have an impact on the process. Therefore, the output itself will not be really a stationary or a steady output. It would have some variation. And it is this variation, when it gets beyond what is acceptable to a customer, we have a quality problem. The customer is not satisfied. In this case, what we have to do is we have to see if we can understand the cause and effect relationship, which is like start with these parameters, start with these factors, and see which of these factors really is an important one, really an influential one in impacting the output. If that happens, of course, you've got at least one handle on the process. It's very possible, of course, that more than one factor would be simultaneously affecting the process. In that case, you have to study that effect also. How do we study these things? We study that by looking at the output and making some deductions based on the principles of statistics and probability. and that is really the objective of today's lecture. I have an example here, and this example basically, I'm going to take a couple of minutes to explain what this example is. It's the optimization of a process using experiments. Now, if you look at, for example, again, I'll give the example of my digital watch. The theory has progressed to the point, as far as digital devices are concerned, when we can write down the exact equation to say what this timing device will show at a particular moment in time. We can relate that to the crystal vibration, the volts, and all the devices that are inside, the little tiny transistors that are inside. We can relate the output to the characteristics of those devices, and we can write down the exact equation for it. Now, that's a pretty high level of knowledge. Generally, this is not true when you go and operate a plant, for example. A chemical plant, or a steel plant, or a mechanical plant, or producing widgets and so on and so forth, or a metallurgical plant. Many times we are really not that sure about the running of that process when you compare that to the state of knowledge that we have with my digital watch. Therefore, what we have to do many times, we have to do experiments. We really have to run that process under different conditions, and these conditions are changed by changing the input parameters. Then of course you look at the output and you try to see what is the effect that turns out to be most prominent and which factor is causing it. If you can get that cause and effect relationship, then you know that this is causing that, and therefore by controlling the input, I'm able to control the output to the desired value. This is really our goal. How do we do that? Let's take a look at the screen again. I have a scheme here, and I'm going to explain this to you later, but I'm just going to show you a matrix scheme, and this matrix scheme, I've got three factors involved. This is some process. This is some process that has got three factors affecting it. And this is, of course, at this stage speculative. We do not know exactly how does factor A impact the output, or how does factor B impact the output, how does factor C impact the output. That we do not know. What we do know is A is a factor that can be set at two levels, low and high. B is a factor that again can be set at two levels, low and high. And C is a factor that can be set at two levels, low and high. So in fact, now I have a means to set the setting of A either at low or at high. I can do the same thing for factor B. I can do the same thing for factor C. In other words, now 2 times 2 times 2. I can produce 8 combinations. I can produce 8 combinations, 8 different ways I can run this process and observe the output. The result is this: A will have its own impact, B will also have its own impact, and simultaneously C will also have its own impact. This is going to show up in the experimental data. So what we have here, we have experiment number 1, which is like when A is set at low level, B is set at low level, and C is also set at low level. So this is the point where I've got factor A set at low level, factor B set at low level, and factor C at low level, and I observe the output. I do the same thing by changing A from low setting to high setting, and again I run a trial which will be done at A at high level, B at low level, and C at low level. So I've got high, low, low. That is the point, this point, and again I run the process and observe the data. In this way, I'm able to produce 8 different pieces of data, 8 different conditions under which I've run the process using 3 factors and at 2 levels each. So I produce this data. This data is highly valuable for us. This is the data that now contains process information. What we then do is we subject this data to some statistical analysis. Statistics actually is the science for analyzing data. Statistics actually is the only science with the help of which you can analyze data. You cannot do that with geometry, you cannot do that with geography, you cannot do that with physics, you cannot do that with English or any other subject. Statistics is actually the subject with the help of which you can analyze data that you produce as the result of some experiment. So I've got this data there, I do the analysis, and the object of my analysis is to find, for example, the very first thing, factor effects, which really says, does factor A have a significant effect as far as the output is concerned? Does factor B have a significant effect on the output, or does factor C have a significant effect on output? And is there any interaction between A and B and C? If that is also there, we also have to find that. So what we try to do is, we try to do the data analysis in such a way that it exploits the structure of the matrix experiment, and it produces these information, these pieces of information for me. What are these little graphs here? On the y-axis, I've got response plotted, On the x-axis, I've got the first block is for factor A at low level and then at high level. And I notice here when factor A is moved from its low setting to high setting, response goes up, which is giving me some cue as to, for controlling the response, I can move A from low to high setting. When I look at B, I find that when I move B from low setting to high setting, response comes down. And when I look at C again, I find again when I move C from low to high, response comes down. Now here, if my goal was to try to maximize the output, I would be picking the high setting for A plus the low setting for B plus the low setting for C. So high at A, low at B and low at C. This combination is going to give me the maximum output, the highest value for the response Y. That's like something that I did pretty simply just by trying some experiments, doing some data analysis and plotting these little plots here. Similarly, I can also find out about interaction between these two factor effects, between these three factor effects. And also I can find out, by doing this, I can find the significance of these effects. By significance, I mean, if I run a trial, if I run an experiment, for example, I'll be doing an experiment right now. This room is relatively quiet, and so there is a low level of noise, and therefore you can hear my voice, because my voice is significant when you compare that to the background noise that is there in this room. But suppose I start lowering my voice, which I'm going to do just now. And you can hardly notice if I'm saying anything, because I brought down my signal to the point it's at the same level as the background noise here. What I've really done is I've reduced the significance of my effect to the level when it's not distinguishable from the environment or the environmental noise. Whatever we call the effect of a factor, which could be as shown by these plots here, these are each significant when you compare them to the background noise. Unless it is significant when you compare that to the background noise, we'll probably just say that factor really does not have an effect. It's just like my trying to say something. So if I have very little voice, you'll hardly notice anything, because my voice level or the signal is at the same level as the background noise. We got to make sure when we plot these plots, when we find these effects, they are at a level that is significant when you compare to the noise. Unless you do that, what is the point in controlling that factor? Because the factor has the same effect as background noise. So it's not really going to be active as a control factor. Now say I've got these things done, say I've got these plots done, and I can probably empirically optimize the process by picking the high setting for A, low setting for B, low setting for C. I can probably maximize Y, that I can probably do. But is that really the mathematical optimum? Is that the best possible optimum? Best possible optimums are producible only when you got a mathematical equation and it can be optimized. So you can find the maxima or you can find the minima. It is only under those conditions you can really optimize the process. To do that, of course, it will not be good enough for me to just play with these charts here, these graphs here. I'll have to build what we call an equation. This is an empirical equation, and in the language of statistics, this is called a regression model. Notice here I've got the parameters A, B, C, D. Those factor effects are there. I've got some of the multipliers with this, and I've got really a mathematical equation here, which is probably not as good as the equation that is used to design my digital watch. It's not as good as that, because here I've got a lot of good theory. I've got Ohm's law, Kirchhoff's law, and all those things put into this little device here, in the design of this device. That will not be possible when I'm working with this little equation here, this empirical equation that I constructed, which I call the prediction model. It's really not going to be good enough. It's not going to be as good as the mathematical model that I have for my electrical device, but it's still pretty good. And with the help of this, I can move to the next step, which is like optimize. And in optimization, we do a couple of things. We try to reduce variation, and also we try to reduce defects. We try to cut losses, and also we try to reduce variation. What has been my approach? What has been our approach here? It's been empirical. It has not been like working out the theory and then finding the optimum point. It's not been that way. We've run some experiments with the real process. This is really the approach that is utilized in Six Sigma. Six Sigma is very empirical. It works with a real process. It changes the different settings and the different parameters, different factors, and then it tries to find out which factor is most active, which factor is not. And then it tries to find the optimum settings for each of those factors. And then you get either lower losses or reduced variation. Concepts and probability, there are a variety of things here. I've listed out a few things there. For example, there is the concept of population, which is like any large body that consists of products, or it consists of people, or it consists of books, or any object that is like slightly different from the other. So there may be a particular population of production, for example, like one day's full production could be a population of widgets. Like if I was producing pens, then a full day's production might produce 5,000 pens, and that those 5,000 pens then they would constitute the population. Now, if I were to do quality testing, I would not be able to sample all of them. I would not be able to really test all of them. So what I'll have to do is, I'll just have to pick a handful. I'll pick a handful of those pens. They are coming out of the production. I'll just grab a handful of them, and then I'll start looking at my sample, and I'll examine each one of them one by one, and I'll try to then assess the quality of this to try to make basically a statement about the quality of the full day's production. That's what I'll try to do. So I have population, which is the full day's production, and from that I remove a sample, and I have something that I call a sample. Most of the time in statistics we play with a sample, and in doing that, of course, there is the chance of probability that is there. So we study a little bit of probability. We study something called frequency of the various characteristics, and that's the frequency definition of probability. Then I've got some simple events, and then in real life we have compound events. I'm going to be describing all of them as we go along. So here's a list of things that we'll be looking at. This is the first slide. Then I've got some more details on the way we collect data. Our data may be our data is basically to try to detect two things. Is the process delivering an accurate performance, and is the precision of the process good? That's something that we'll have to find out. Accuracy and precision. And in order to be able to do that, I have to collect data, and the data will have to be measured by some instrument, and it might produce results like categories of data, for example, excellent, good, fair, bad. It could be that way. Or I could rank them from the best one to the lowest one. So that also could be there. Ranking would be there. I could also use interval scales when I really have slots, and in that we dump data. We put some data there, here and there and so on, and I end up with what we call the use of the interval scale. And of course, the most popular one is the ratio scale that produces real numbers. Then of course, when we've got data collected, we'd like to know where does most of the data stand, and this is something that we'll have to do by slowly then getting into the nature of the data that I've collected. So we'll like to know, for example, what is the central tendency of the data? Where is most of the data concentrated? And it is usually concentrated around the mean. And now, because I've drawn a sample from the data, from my population, there will be something called the sample mean, and there will be something called the population mean. Both are there. There is the sample mean, and of course there is the population mean. Generally speaking, the population mean is unknown, and we try to estimate that by working out by calculating what the sample mean is. So the sample mean becomes the estimate for the population mean. There is another way to say where is most of the data concentrated, and that is to take a look at the median of the process. And the median basically is a quantity that has equal number of, in terms of frequency or probability, equal number of items below it and above it. So in fact, again, I'm going to be giving you details on this. I just want you to know that besides mean, there are other measures and that tend to indicate where most of the data is concentrated. And this tendency is called the central tendency of the data. Then of course, we got something called mode, mode is the point where most of the data, they seem to have the highest probability. And again, I'm going to be showing this to you as we get into this. Then sometimes, of course, we trim the tail ends of the distribution that we end up producing as a result of some data collection. And we end up with what we call the trimmed mean, the trimmed sample mean of the data. That's like something that we will do again once we get into this analysis. Now that was the central tendency of the data. Then there is something called the dispersion of the data. How are the data distributed? How are they spread around? Are they really concentrated together when I've got good precision, or they spread around a lot? The measure for this is the measure for dispersion. How we find that out? The very first range is called range. Range is the difference between the maximum value of the observation and within the same sample the minimum value of the observation. So if you've collected 5 pieces of data, x1, x2, x3, x4, and you find that x2 is the highest number, so put that aside, that's the max, and if you find x3 is the smallest number, then that becomes the min. And the difference between x2 and x3, which is the difference between max and min, that becomes the range for that little sample there. Range is also a very good indicator of dispersion of the data. And of course, the data that is theoretically most useful is the standard deviation, is the square root of the variance of the data that you've collected. That also is something that we'll be looking at. Then of course, we've got a population standard deviation, which is sigma, and then we've got something called the sample standard deviation. The sample standard deviation is denoted by S, and that actually is an estimator for sigma. Sigma is the population standard deviation. Then we've got a quantity called interquartile range, which is the range between the third quartile and the first quartile. The difference between the first quartile and the third quartile, that space there is also an indication how widely the data is distributed. All of these are basically dispersion, indications of dispersion. Then I may have a situation when, for example, if you look at my chart here, the normal distribution is like this, symmetric. But sometimes what happens, that the data tends to get skewed. So this distribution could be like this. That's a skew to the left. And this is called actually a positive skew. And it could also be that my skew turns out to be going to the right. And the data could be like this. This is here. I've got most of the data going to the right, and this is called a negative skew. And there are formulas available that tend to tell you how this distribution is shaped. The shape of the distribution would now come from the skewness of the data. So the word here is skewness. There is another way I can represent the shape of the data, and that has to do with, again, when I start comparing that, I have a normal plot which is symmetric like this. That's the standard one. It's very possible that my data is flatter than this. My data is flat like this. Or it is lumped like this. Both of these are different from the standard normal distribution. And these have what we call kurtosis. Kurtosis. Kurtosis is a peculiar property which will be there in a piece of data like this, or a flat piece of data like this. And this is something we got to keep in mind when we are looking at data. We should not be using the normal distribution theory. We should be using some other theory that would be appropriate when you got a situation like this. So just to give you an idea, I just plotted these two little graphs there, and I gave you some indication of skewness and of kurtosis. Now it's very possible, many times what happens, you have data, and the data basically can be plotted. There may be two variables for which I have collected data, and my data can be put on a scatter diagram. And the scatter diagram goes like this. This is x and this is y. These are two different observations, and this could be, for example, sale of coffee, and this could be temperature. Sale of coffee at the coffee shop, and this could be ambient temperature. You might find when I do this, I tend to find a scatter plot which is like this, which will be like this. Actually, this would be probably true if temperature is high this way and low this way, then this would be the sale of cold drinks. As temperature becomes low, the sale of cold drinks also becomes low. And as temperature goes up, the sale of cold drinks would become high. So these two variables then, they rise together and they fall together. This is a scatter diagram. To try to make sure you can see them, I'm just going to circle a few of them, and you'll be able to see the scatter a bit more clearly. These are little flies, and they tend to be rising together and falling together. You see that scatter there? Now, it's very possible that underneath there is some relationship, that is the relationship between x and y, and that probably could be represented by a little model like that. So, first we draw a scatter diagram. We take any pair of data. It could be height and weight of people. It could be anything else. You've got two data that might have some relationship, and in order to discover that, what you do is draw a scatter diagram, and you end up with this little diagram. If it shows this sort of tendency, then you go for regression. Then you try to fit y as a function of x. It could just turn out to be this: y is a plus bx. This then becomes your predictor equation. Given some value of x, you are able to predict y. A and b are the parameters of the model. This is also used a lot when you are trying to optimize something. And this is actually indicating association. But notice here, not all the points are straight on that directly on the straight line. There is some variation. There is some variation around this. And that variation actually reflects the effect of not only x, but perhaps other factors, which also might be impacting y. Therefore, what we have to do is, we have to work out something called the correlation coefficient, or the covariance of x and y. If the covariance is 1, if the covariance is really high, then of course you would say that I can predict y perfectly given x. But if it's less than that, then I need to have more terms in this model in order to be able to predict y as precisely as I would like it to be. If that is the situation, we'll have to really collect more data, and perhaps collect data on the third front also and fourth front also, and our regression is going to be then more complicated. But it can be done. It's done all the time. This is the empirical way to build a model. This is like using experiments to construct a model which eventually would look like my digital watches, that fine equation that the electrical engineer worked out. Correlation coefficient, of course, is a term that is used a lot, and before that I have what we call covariance. The correlation coefficient, it goes like this. It has got covariance x, y divided by sigma x and sigma y. What is this term? This term, if it is like 1, then you will say x and y have a strong positive correlation. If this is minus 1, which will be the case when I've got x and y going the other way, if it is minus 1, then you will say that x and y, they move opposite to each other. And in many cases, of course, x and y are not related, in which case you will probably find rho to be such that sigmas are the only ones that dominate. When you look at sigma x and sigma y, you find that rho turns out to be pretty close to 0, which means there is no dependency of x and y. Let me write rho there in place of sigma. This rho, if it turns out to be close to 0, there is no relationship between x and y. So this is again something that is useful if I am using one variable to try to control the other. And this is what I indicate by saying that correlation can be plus or it can be minus. And I have already discussed about regression, which is really a model like this, which will be a model like this. This is a simple regression model. More complicated models, they will have more variables. These variables on the other side, they are on the right hand side, they are called independent variables. And this guy is called the dependent variable. A and B are the parameters of the model. Then of course we got the idea of probability and probability distributions, and let's quickly take a look at these things. We have something called random variables. I'm going to give you some examples here. Random variables are variables that depend on events. So you could probably say, if a girl enters the room, I mark it as 1. I mark the value of the random variable as 1. And if a boy enters the room, I mark the value of the random variable as 0. Here, by counting up number of 1s, I can find out how many boys have entered. And by finding out how many zeros are there, I can find how many, and so on. So this can be done quite easily. If this is done, I have a measure now. And if the events, if the arrivals of the girls and boys is random, then of course the output is going to be also random. And the random variable now, that is indicating the kind of people who are walking in, and that's being indicated by 1 being girl and 0 being boy. I'll end up with here a random variable that will be influenced by probability. It will be influenced by some randomness. And this randomness would depend on the kind of people who are walking in. I could have a continuous random variable, many random variables like height, weight and so on. Those are continuous. And I could also have discrete random variables, in which case I am basically counting some event and I am looking at the count as the value of the random variable. In this case, the random variable is going to have discrete value. It will be called a discrete random variable. If you look at the tossing of a coin, that's an event that has got two outcomes, head and tail. When I toss it, if I toss it a large number of times, then of course I end up with an estimate of the probability of my finding, the likelihood of my finding a head when a random toss is made. This is good because I've collected a lot of data, I can rely on it and so on and so forth. So I probably tossed 500 times and I found the number to be pretty close to 0.5. Maybe it is 0.501 or it's 0.497 or something, which is pretty close to 0.5, and I've got an estimate there. Tossing a coin can lead to complex situations also. For example, if I toss three times, what is the chance of my finding no heads? What is the chance of my finding one head? What is the chance of my finding two heads in the last two tosses? The first one being tail. These are complex events and the probability of these can also be found. So in fact, what I have to do here is I have to find a method. Just like we have plus and minus and multiply and divide to play with numbers, I must have a system now to play with probabilities also. So we can add probabilities, we can multiply probabilities. I need a system for that. For that I need some ground rules. These ground rules are called postulates of probability. These have been given about 100 years ago. More than 100 years ago, these were worked at. Just like the number system, it came 1,000 years ago, more than 1,000 years ago. So probabilities also were looked at, and 100 or 200 years ago, people worked out the algebra for probabilities, adding and subtracting probabilities. Tossing a die. Now a die, as you know, it's a thing that has got 6 heads. So if I draw a little die here, it would look like this. This is the die. And the distinct thing about the die is it has got 6 faces and it will have certain number of dots on all sides. So I could have 3 there, 5 here and 2 here. These are the different faces and they have these different numbers there. When I toss a die, when I throw a die, the chance of the number being read being 2 or 4 or 6 or 5 is going to be 1/6 because the die is symmetric and the die, when it's tossed, it's thrown randomly. So there is no likelihood of 3 being there all the time. It could be any number between 1 and 6. What is the chance of my finding zeros here? The probability of my finding a 0 reading there is 0 because there is no face with a 0 with no dots there. Similarly, I can't find a number 9 there because it is just not there in the sample space. What we have to then do is we have to really define what we call the sample space in order that we can go out and start defining probabilities. So we have something that we call the sample space, and again I'm going to give you some examples there. Then we'll discuss something called the probability distribution function. We'll have a probability density function. We'll have a cumulative distribution function. We'll have something called expected value, which is really the average. We'll also have something called variance. And these are values that are realized by looking at data that I collected when I was collecting the sample. If you collect a lot of data, then it turns out that the data itself begins to take some shape. And let me give you some examples. Let me give you examples of the kind of shape data might like to pick up. In some cases, the data may take a shape like this, which is the normal distribution. In some case, when you do, and what is this data really? You really will not find a continuous curve, but you'll find what we call a histogram. This is what you find in real life. So this is actually, these bars are a histogram. If you take lots and lots of data, eventually it will begin to look like a continuous curve, and that will be the distribution that will represent. So this histogram is an approximate representation of the real distribution that is there. And this will become apparent as you collect more and more data. So some processes, they lead to this sort of symmetric output. There are other processes that lead to this sort of output. And let me just give you a picture here. So what is the shape here? The shape here would look like something like this. This is the exponential distribution. So it's a different distribution. There are many other distributions. Some look like this. Others have some other shape. They could be like this, and so on and so forth. So there are a variety of different distributions, and these are all found in nature. And that's why people came up with different types of probability distribution models. Like, for example, there is something called the hypergeometric distribution, something called the binomial distribution, something called the Poisson distribution, normal distribution, and so on and so forth. These are all useful in studying random phenomena. Whenever you collect data, it will probably conform to one of these things. And there is a lot of very rich theory available with each of these distributions. And basically exploiting that, by exploiting that, we can make statements about a process that is driven by, let's say, the binomial distribution or the exponential distribution or the normal distribution. In quality assurance, and in particular when you're going to be working in Six Sigma, you'll probably have to know some of these distributions in order to make statements which others can also come back and reproduce. That's something that we'd like to be able to do. Then, of course, many times we've collected some data, but we do not know what the true mean of the population is. In that case, we'll have to do something called inferencing. Inferencing basically says I've collected a certain amount of data, and I'm going to be using that data now to come up with some estimate of the true mean, which is mu. I could do the same thing for variance, and I could do the same thing for difference between means or the proportion of parts that are defective in production. In fact, we have many different measures that can give us pretty decent ideas of the about what we call defects, distribution of defects, or the kind of problems that we are having in a particular situation. There are some special situations when we'll need to do some testing. Tests are basically mathematical processes. These are mathematical tricks or methods which are utilized to make sure you really have a decent idea of what the true mean is. So I may have a quantity, like for example, if I had x bar calculated from sample that I collected from this normal distribution. I calculated x bar. How close is this x bar to the true value mu? How close is this? This statement I can make only when I apply what we call inferential statistics. So there is some theory there that we'll be utilizing to be able to say with some confidence that I'm 95% sure that the value of x bar is such that around x bar I can put a band, and there's a 90% chance that this guy is in that space. There's a 90% chance that around x bar I can put a limit between a and b, and there's a 90% chance that the unknown mu is going to be residing there. There's a 90% chance for that. That means if I repeat this process of calculating x bar 100 times, most likely about 90 times out of 100 times, the true mu is going to be within that. That's the idea. This is like one statement of inferencing, and we do the same thing for variance and for different parameters that are also unknown. If we move along, we also have this idea of test of hypothesis. For example, if we wanted to say, for example, the first example that we had when we had the, I'm just going to bring that up. This diagram here, does A have an impact on the process? Does factor A have an impact on the process? This could be posed as a hypothesis or a guess. There is a way to collect data. There is a way to change the settings of A and look at the output. And there is a way to test the data, and this data testing will tell us whether it is reasonable to assume that A has an impact on the process or it does not have an impact on the process. The statistical procedure here is called test of hypothesis, and that's what I have here in the slide here, which is the test of hypothesis. And there I set up certain conditions, and I call them the null hypothesis and the alternate hypothesis, and then I carry through a process. I carry through a data analysis process, and that process ultimately comes back and tells me, yes, indeed, there is reason to believe that A has an impact. Or, no, I do not see the evidence that A has an impact. Because whatever A is doing, noise is doing the same thing. It's like Dr. Bagchi is trying to say something, but perhaps he is not saying anything, because what he says, if there is no sound, if there is no signal that is above the background noise, you'd probably say Dr. Bagchi is quiet, he is not saying anything. There is no signal. Factor A has no impact on the process. And these, of course, these different tests, they have different applications, and they would come as one-tail test or two-tail test, and they involve something called the type 1 error, a type 2 error, and so on and so forth. As we get deeper into this subject, you'll find I'm utilizing these ideas, these concepts, and I'm doing the t-test sometimes, I'm doing the f-test sometimes, I'm doing the chi-square test sometimes, and sometimes I'm doing a plain and simple z-test. Those we'll be doing as the time comes along. Now, what is probability? Why do we study probability? You see that phrase there. You see a phrase there called stochastic. It's a very, very important point. It's a very important phrase. Stochastic means random. It's a fancy word that the learned people they have used. Random is a word that normal people use. You and I would use the word random, but if I were speaking as a professor, I would not call it random, I call it stochastic. So a random variable is also a stochastic variable. So please don't be flustered by this fancy term called stochastic. It means the same thing as random. Now, we have many, many decisions, and these decisions are generally based on events that cannot be predicted exactly. Under such conditions, we still cannot escape decision making, but we are doing this in an environment that has got a lot of uncertainty in it. In that case, we'll really have to rely on the theory of probability. We'll have to rely on the theory of odds, and not just simple coin toss, but also some rather complicated situations where the events are interdependent, the events have conditionality, and so on and so forth. Many other complications are there with random events. And that's what we'll have to do in order for us to be able to make sound decisions. And of course, when I'm banking all of these things on data analysis, I'll probably observe something, or I'll conduct some experiments, I'll collect some data. That data will be subjected through what we call data analysis. Once we've done that, we'll have some idea about the randomness, we'll have some idea about the stochasticity of the process, and then obviously our results are going to be far more reliable. Where do you apply probability theory? Let's take a look at this. Well, many of you have probably done forecasting of some sort. Forecasting is one place where you apply both statistics and probability. Inventory management, when you're trying to decide on the safety stock, for example, there you'll be using probability, and also you might be using some statistics based on past history and so on, fluctuations of past demand and that kind of thing. Quality assurance is one area that cannot escape probability and statistics, because in real life, when you've got a real factory producing things, there are many factors that are not in control, therefore the output is variable. Once the output is variable, to try to keep it confined to values which the customer is going to accept, I'll have to understand this randomness, I'll have to understand this stochasticity. And of course, for this I may use a control chart to plot it, I may use what we call sampling, I may use design of experiments, I may use multiple regression modeling, and so on and so forth. So a variety of techniques which are now borrowed from statistics, though are utilized by people who are doing quality assurance. And of course, Six Sigma uses DOE, design of experiments, in a very big way. Project risk management, this is like one large area where things can foul up, and this is by Murphy's law. Whenever you've got a project, it's very possible that certain assumptions will not hold true. For example, you're going to be building a factory, and you're counting on the demand, market demand, to be rising and rising and rising. If it does not happen, then of course your project is going to be a failure. But demand is not a linear function always. Demand will have some fluctuations. It will probably begin somewhere, then it will begin to fluctuate and fluctuate and fluctuate and so on. So to somehow catch this, I have to somehow understand this fluctuation. And on the basis of that, I'll have to come up with a risk management plan. So whenever I've got a project going, I must do risk analysis. And risk analysis strongly depends on probability theory. There are some special methods, and we may get a glimpse of this toward the end of this course when we discuss Six Sigma projects. We might come back and discuss a little bit about project risk management. That we might do. Investment portfolio design. Just this afternoon I was speaking with a senior professor, and he said he's got about 50,000 rupees in his pocket, and he would like to design a stock portfolio to be able to protect his investment and at the same time generate some good returns. Now, so his task is now going to be, the marketplace consists of all kinds of stocks. They have different types of returns, they have different types of fluctuations, variations and so on. And what you'd like to be able to do is somehow balance this risk and return. And for that, you'd have to optimize the composition of this portfolio. So that's like another area where we would be using probability and also would be using statistics. Those are also utilized there. Business simulation is one large area, and market research. These are large areas where we use a lot of statistics. Game theory is a big area where strategies are found, and this is actually an area that uses probability in a very big way. And I already mentioned Six Sigma uses in one of its steps, and I'm going to write that again. It's called DMAIC, D-M-A-I-C. Define the problem, the issue that you want to tackle, measure, analyze, improve and control. It is the improvement step where I bring in statistics and probability. I actually bring in what we call design of experiments. So DOE is used right here, and DOE comes from statistics. Statistics gives us DOE. So if I'm trying to use the DMAIC framework, I'll not be able to escape statistics. I'll have to use it in one form or the other. I will be discussing some of these things. I'll be discussing outcomes, I'll be discussing random events and so on. I'll be elaborating that as we go in the afternoon, as we go deeper into this. But let's try to get an idea of what all various things we'll be discussing. I'll be discussing something called what exactly is probability, what are some of the basic rules for combining probabilities, for adding them, for multiplying them and so on. What are conditional events, what are compound events, and how do I work out the probabilities for compound events or conditional events. We'll also get a glimpse of the distributions. We'll also try to get an introduction there. And also we might get a glimpse of what we call hypothesis testing. That also we'll try to attempt. That's a lot of things, and we'll see what we can get to. To begin with, what exactly is probability? This is something I'd like to, we are reaching the end of this hour, and I'd like to make sure you have some idea of what is probability before we end here. It's the study of chance associated with the occurrence of events, and these events are actually random events. It's the study of chance. That's what probability theory is. And what kind of probabilities are we talking about? We may talk about probability. It's like the chance of a rain when it's cloudy, and people who have some experience with monsoon clouds and so on, they may look at the color of the cloud, and based on, they may say there's a 50% chance it's going to rain, or the 80% chance it's going to rain, or there's a 5% chance it's going to rain. This sort of statement is not based on really hard data. It's based on subjectivity. And this is really the basis. Many times this is the only basis for working out probabilities. Sometimes what we do is we construct a theoretical model, and on the basis of the theoretical model we make predictions about the probability of complex events. That we do. If I'm not able to do that, I'll probably have to sit down and collect a lot of data or run some experiments, and from that figure out the probability of certain events. So to try to estimate probabilities, first of all, what are probabilities? Probabilities basically are a study of any event that can occur by chance, and we are interested in the outcome of that experiment. There are two ways I can measure probability. I can measure probability either by theoretical considerations, and I'll show you how to do that, or I can measure probability by relative frequency, which is like by calculating based on hard data, calculating the odds. That also I can do. Rolling a dice. Now here I do not really need to toss a lot of coin or a lot of dice. I don't need to do that. Here I can directly say that based on my experience, and based on some little principles of probability theory, I can make a statement about if I roll the die 2 times, what is the chance that the sum of the two numbers that I see, the first number and the second number, is going to be equal to 4. That I could do just based on my experience. I could do that. And I'm using some classical theory here. So how could I get a number 4? I have 1 plus 3, or I have 2 plus 2, or I have 3 plus 1. Of course, I can't have any other number, any other pair of numbers that will add to a sum of 4. Because none of the dice would give me 0. If I had 0 plus 4, of course, we'd have another way to find 4. But that's not happening here. I've got 1 to 6 on the first die, and I've got 1 to 6 on the second die. So I can add to get a sum of 4. I can have 1 plus 3, or I could have 2 plus 2, or I could have 3 plus 1. These are 3 different ways. Now, finding a 3 on a dice, finding a 3 is 1 by 6. And finding a number which is 3 on the first dice, 1 on the second dice, that's also going to be 1 over 6. So here the chance of rolling a die, 1 by 6 is the probability of rolling the first die and finding number 3. And 1 by 6 is also the probability of finding a number 1 on the second die. Therefore, for the two of them to occur together to give me a sum of 4 is going to be 1 by 6 multiplied by 1 by 6. That's 1/6 multiplied by 1 by 6. That's a simple calculation that I could do quite easily. It would turn out to be 1 by 6. So one way to find 4 is going to be probability 3 plus 1. And these are on 2 different dice, so therefore it's going to be probability of 3 and probability of 1. At the moment I do that, the probability of first one is going to be 1 by 6 multiplied by 1 by 6. Notice here, I've used a little bit of algebra, and this algebra came from this notation. And here what I've done is I've got really the probability of this guy, 3 and 1 calculated. I wrote it loosely like this, but really I should be writing like this. And the probability of this event, 3 and 1, is going to be 1 by 6 and 1 by 6, which is 1 divided by 36. That's the probability of my finding a 3 plus 1 sum. I could do the same thing for 1 plus 3. I could do the same thing for 2 plus 2. These are different ways by which I could construct my event 4. The sum of the numbers on the 2 dice to be equal to 4. So here what I'm doing is I'm using some classical theory. I could do the same thing for coin toss. I could define the coin toss in a manner when I have a certain number of heads in a number of trials. Like if I throw it 10 times, what is the chance of my finding exactly 3 heads and 7 tails? I could work this out using classical theory. Let's get down now and very quickly define what we call sample space, events and random variables. This sample space actually is the set that consists of all the outcomes. For example, when I'm tossing a coin, there are only 2 outputs possible, head and tail. So the sample space here consists of head and tail only. So all I really have, I have head and I have tail. These are the only 2 outcomes when it comes to tossing a coin. These are, by the way, event. The finding a head or finding a tail, observing a head or observing a tail, these are events, or the coin appearing on head first, that's going to be an event, and tail is going to be also another event. And these 2 events, I'll tell you later, these are disjoint and they are also mutually exclusive. There is nothing common between these 2. If I have an event which is random, I can talk about the probability of that event. For example, in coin toss, probability of finding head or the probability of finding a tail, in this case is going to be, the probability is going to be 0.5. What I could do is, I notice here, I've got the sample space which I have, in the diagram I marked it as S. The sample space consists of all the outcomes. So in the head and tail case, I'll have a head sitting there and also a tail sitting there inside the sample space and nothing else. Now I could define a random variable. Based on that, I could define it to be X, and I could map head to 1 and tail to 0. So I'll have a little mapping done here. head will be mapped to 1 and tail will be mapped to 0. And these are the values of the random variable. These are events, and from the events I ended up defining this random variable. And this is what I will be doing as we move along. We will be defining many different events, and we will be defining the obvious and the associated random variable with it, and we will end up with real numbers 1 or 0 or any other number that will turn out to be, that it's going to turn out to be. I'm going to continue this. I'm going to continue this talk as we go into the next session. Thank you very much.